All right, for this third example, I have f of x is the absolute value of x if x is greater than -2, and x squared minus 2 if x is less than or equal to -2. So let's draw our line at -2. That's where we're dividing our domain in half. If x is greater than -2, it's absolute value of x, so I have to find that on this side of my domain. And I like to label them like this on the top of my graph because it helps me remember which function's defined where. And then if x is less than 2, or equal to -2, sorry, that's a typo on my part. Let me fix that now. Less than or equal to -2, it's x squared minus 2. X is less. Okay. So if x is greater than -2, I've got absolute value of x. And it's important to note that -2 is not included because it's greater than, not greater than and equal to. So I've got to put a circle there. So we have our absolute value function. Then I have x squared minus 2. Well, I know that's going to be a regular parabola, right? Just shifted down 2. So I'm actually going to test some values into that function to make it easier to find how to graph it as opposed to drawing its picture and then erasing what's on the wrong side of the domain. So let's pick when x is -2 and -3 to give me a couple points to graph a parabola. Typically, I'd want 3 points to graph a parabola, but its vertex would have been like right here, right? And now we aren't going to have a vertex, so 2 will be okay. You need 2 points, including the vertex. So here I have y. Nope, that's an eraser, y. So if I have -2 squared minus 2, that's 4 minus 2, which is 2. If I have -3 squared minus 2, that's 9 minus 2, which is 7. So I have when x is -2, y is 2, and that's included, so I can plot that right there. Oh, I'm filling in that spot. Interesting. And then I have when x is -3, y is 7, 2, 4, 5, 6. 2, 3, 4, 5, 6, 7. There we go. So here's my parabola. So this is actually continuous. That's kind of cool, right? I could draw this without picking up my pencil. That happens sometimes in piecewise functions, but that's not always going to be the case, so keep that in mind. My domain is all real numbers, and my range goes from 0 to infinity. I didn't write my domain correctly. There, that's kind of better. Last, we've got a three-parter. So if x is less than 0, my function is defined by x squared. So here's where x is less than 0. I've got x squared. Between 0 and 3, inclusive, I have my function is defined by 2, right? That's a constant function. 2. And then I have, let's rewrite that as -x plus 4. So we know we've got a negative slope and a y-intercept of 4 when x is greater than 3. So let's go ahead and graph these three functions. So I've got x squared, but 0 is not included, so it's going to be an open circle. We're really good at graphing the squaring function by now. I have f of x is a constant between 0 and 3 inclusive, so it's 2. So 1, 2. So my endpoints are included, and I've graphed this line. Okay. Then I have -x plus 4. So here I have 3, 4, 5. Let's find some points on this line as opposed to graphing it and then having to erase. I think that would be best. So I have, if x is 3, I have -3 plus 4, which is 1. If x is 4, I have -4 plus 4, which is 0. And if x is 5, I have -5 plus 4, which is -1. So I know this line is not defined exactly at when x equals 3, so it's going to need open circle at 1. When it's x is 4, y is 0, and when x is 5, y is -1. So this does have negative slope. It's always good to check that the graph makes sense. So my domain, again, is all real numbers. It's defined over every point on the number line, as well as my range. Because if I go through and I start down here, right, I'm defined by this function, there is some overlap, but I have every single value of y represented. So it goes from negative infinity to positive infinity.